Going good?
Feeling good?
Yeah. Let me find a second.
Okay, hello everyone. It's my pleasure today to introduce Lucas Colley. He is a maintainer of SciPy, Pixie, and Array API, all while still doing his undergrad, studying computer science and philosophy at Oxford. I think that's mighty impressive, and also kind of makes me feel like I underachieved in my own life. And he's going to introduce us to the Array API ecosystem, which is this effort to unify all the different API libraries in Python. So yeah, looking forward to what you have to say.
Yeah, thank you very much for that great introduction. Yeah, let's just jump right in. There is a QR code here if you would like to scan it to view the slides, but the link is also in the footer to the webpage. You can also just find that at any point. Yeah, we're talking about the Array API standard, and let's go. Just to say a few words about me. I guess this has already been said in the introduction. Yeah, the one thing that wasn't said is that I'm currently working at prefix.dev for European Summer of Code, and yeah, working on Pixie there. So the agenda for today, the talk's split into 3 parts. To start off, I'm just going to try and cover everything you need to know if you've never heard of the Array API standard before. So what is kind of the idea behind this talk, why do we care about it, and what is the high-level solution that's being worked on. In the second part, we'll make things concrete and go through all of the different GitHub repos that are involved in actually making this solution. And then finally, I'll cover some status, what's changed over the past year, and what are we going to do looking forward. Okay, brief introduction to arrays. I'm sure all of you have at least used NumPy before, but when we're talking about arrays, we're specifically talking about this n-dimensional grid-like data structure. NumPy.NDArray is the most famous one, but there are actually lots of other types as well that implement this same data structure, as we'll soon see. It's not just any grid, it has some restrictions. So it has a rectangular shape, which means it's kind of full. You don't have like different rows of different sizes. That would give you a different data structure. Also, each element in the grid is of the same data type. And these restrictions are helpful because it means that we can have really nice, fast, easy implementations of lots of different functions that can do all sorts of things on these arrays. This is just from the NumPy documentation. You probably see some libraries you've used or worked on there. Yeah, they're all over the place. Here's another way to look at the array ecosystem. Like I said, there's lots of different types, not just NumPy. This diagram is a few years old, so there's actually even more different types now that might be used. Maybe some of these aren't used so much anymore. At the top, you see these array libraries, what I'll call from now on array libraries. They're also called the providing or provider libraries. They're what are giving us this data structure. And there's a few of those, and then there's lots and lots of libraries that they don't make this data structure, but they make use of it. And we can see that the ecosystem is kind of divided into all of these sub-ecosystems, where you have a bunch of libraries, a stack that will work with NumPy, and you have a completely different stack that will work with PyTorch, things like this. And the idea behind this talk, at a very high level, is removing these barriers at the bottom here. In general, we want to work on interoperability between these different sub-ecosystems to a point where end users can start picking and choosing libraries from different ecosystems, and they'll be able to pick and choose which array type they want. And yeah, this shouldn't be too difficult. We're not literally trying to get every single library down here working with every single other one. Some of them are doing things that are very specific to an array type. They're doing things that are only possible because you use PyTorch or so on. That's not really what we're talking about here. We're talking about libraries that just take arrays. And maybe they just happen to be implemented in PyTorch because of the domain that they're in. A lot of other things in that domain also use PyTorch. But actually, the functionality that they implement just uses arrays. And it would be nice if users could use them with any type of array. Yeah. So hopefully that's given you a brief idea. I'll just go into a bit more now about motivation. Like I said, end users, it would be nice if they can switch array libraries without reinventing their entire stack. For example, a reinforcement learning lab, they might be shifting their core pipelines from PyTorch to JAX. And okay, that's going to be work in itself. The things that they're using for their reinforcement learning might be very specific to things that only exist in PyTorch and JAX. But the part I'm interested in is all of the rest of their stack. Maybe they have lots of other tools, lots of other scripts around their stack that are not doing anything that's specific to one array type. They're just using arrays in general. And it would probably be a lot of work for them to convert everything, find out, okay, I did this with the PyTorch ecosystem, but how do I do this with the JAX array instead? And maybe they find that something is implemented, but it has some caveats, or it's not implemented at all, and they have to make it themselves. And yeah, this is not a nice experience. So we would like to change that story. Of course, one thing they could do is just say, okay, I've shifted my core pipeline to JAX, but for everything else, I'll just convert the array type back to PyTorch and use whatever I was using before. But that can be a problem. When you're switching between array libraries, and especially between devices, that can be very slow. If anybody was in Jacob's tutorial yesterday, you'll have seen a real example of that, where it can be slow when you're moving things between the CPU and the GPU. And if you have some sort of production pipeline, you're not really going to want to be switching between array libraries all the time, if you can help it. We also just want to enable experimentation. You shouldn't need some big polished pipeline to want to try out new array libraries. Maybe you just got a GPU and you just want to see what it would be like if your NumPy pipeline could work on that GPU. Or maybe there's some cool new library that only works with PyTorch, but you've never used PyTorch before. Again, it should be nice and easy to try and integrate that into your stack. Okay, now also for array consuming libraries, as a maintainer of SciPy, I know that we get lots of requests from users for hardware acceleration. They would love it if our code works on the GPU. They'd love it if it worked with this PyTorch library that they just heard about. And yeah, we would like to support that. However, we don't want maintenance burden increasing massively. If it was going to be 3 times the effort to support 3 libraries, then it would just be impossible. We couldn't do this. And that's for a big library like SciPy. Of course, lots of smaller libraries, it's going to be even more impossible to take on this extra maintenance burden. And another thing, you shouldn't really have a library dying just because the underlying array library it uses falls out of fashion or doesn't get updated anymore. Let's say in 10 years' time, nobody's using NumPy anymore. I don't think that's going to happen, but let's say it does. It would be a shame if all the work that went into SciPy is just gone, and okay, you can't use it anymore. So any consuming library that wants to kind of loosen their dependencies a bit and just depend on arrays in general, that's a bit safer because I don't think arrays are going away anytime soon. Also for array providing libraries, why might NumPy or PyTorch care about this? Well, for these existing libraries, it means that they'll get interoperability with new libraries if they're written to support this standard. And also, API decisions can be made collaboratively with other libraries. If we're all agreeing on one standard, then we can have knowledge coming together and making the best decisions. But perhaps the most interesting thing is for new libraries. Let's say there's a brand new device came out and you're tasked with making the array library for that device. It's nice to have a standard specification, a concrete API to implement. You don't just have to look at the whole of NumPy and try and guess what users might be interested in and what they might not be. When you do implement that concrete API, you then get compatibility with libraries that have supported this standard. And final bit of motivation is a more holistic ecosystem view. This is an excerpt from my slides last year, where we have some functionality and we have different array types here. So imagine one of these is NumPy, one of these is PyTorch. Maybe you've bumped into this yourself if you've tried experimenting with different array libraries. You'll find something that works really nicely with one array type. Maybe it pretty much works with another one, and then there's another one where there's no implementation at all, or something else, you kind of need to do half the work yourself. And we would like to change this picture to look a little bit more like this, where we have array-agnostic implementations. These are implementations that can take in all of these array types and automatically give out the same array type and do the computation native to that array type. And the good thing about this is that we go from 4 different implementations to 1, and hopefully that will reduce the amount of duplicate work that happens and also reduce maintainer burden in the long run. So that's kind of the magic array-agnostic implementations right now. The rest of the talk is going to be going into a bit more detail about what this thing is. Okay, so that's the problem. What is the solution? I made this diagram yesterday, and I think it can be somewhat helpful to explain. Basically, we have 4 stages in this solution. At the middle, we have the first stage, which is the API. We need to decide what is this standard API, what is this thing that all of these different libraries are going to agree we should implement, what is an array, which functions do we need, and which ones should we leave behind in the past. The second stage is actually getting this implemented in libraries. So we have NumPy and PyTorch there, and there are lots of others. Actually getting these to adopt this standard API to the point where other libraries can use it. The third stage is we have SciPy and scikit-learn there. This stage is representing the kind of core libraries in the ecosystem that lots and lots of different array consuming libraries will depend on. It's no good having maybe the library you maintain try and adopt the standard if you have a dependency on SciPy and SciPy doesn't support this. So we kind of first of all need to get the core libraries converted, and then the final stage here, the outer ring, is just representing any smaller library that maybe you maintain yourself and could start adopting. And we'll come back to this a bit later to talk a bit about where we are now in these stages and where we're going. But who is actually taking on this work? We're working on this as part of the consortium for Python Data API Standards. It's been working on this for 5 years now, and the consortium has members from across the ecosystem, from each of the big array libraries. There are members, and also representatives from big consuming libraries as well. And yeah, this consortium has been working for a long time on creating the API standard itself and making these decisions. And now there's a lot of work on implementation and getting this adopted. Okay, so hopefully you all at least have some sort of understanding of what the problem is now and how we're going about it. Now I'd like to go into a bit more detail about the repos that are actually making this possible. So we're going to be talking about 6 here, starting with the Array API itself. So when people say the Array API standard, this is what they're going to be talking about. It's basically a website. It has a lot of narrative content, talking about some of the things that I've already mentioned, also talking about design decisions and things like that. But the most important one here is the API specification. This has all of the different functions that we're saying this is what you need to kind of count as an array, all laid out into different categories. And each of these pages will have things like this, where for each function it tells you, okay, this is the signature it should have, these are the types it should take in and give out, and this is the behavior it should have for when it gets this input. So an array library like NumPy can look at this and it can check, okay, I think we're doing that already. Hang on, this is slightly different to the behavior that we've already implemented. Can we change this? And a brand new library, this gives them a nice recipe of, okay, this is what we need to implement. We just need to figure out how to do it in our framework. And it also tells consuming libraries what they can use. So in SciPy now, when we're working on new code, we don't really need to look in all of these different places. What is NumPy doing? What is PyTorch doing? We can just look in the standard and see, okay, this is the function that I need to use if I need to do this. Then there's a lot more to say about the standard here, but most of it has been covered already by a talk from Aaron, another member of the consortium 2 years ago at SciPy. This is on YouTube, so I'll definitely point you towards this if you'd like to hear a lot more, especially about past work that was done before this initiative, also the design principles that kind of make this a bit different to things that have been tried in the past, and the methodology of how they actually went about creating this standard. But let's move on. We have Array API tests next. This library is completely facing the array libraries like NumPy and PyTorch. It gives them a test suite that they can use to check that they are implementing this standard. So, for example, this is running in NumPy CI right now. If a contributor sends a PR to change some behavior, and actually this behavior would contradict something in the standard, this is going to be caught by CI. So we have a nice way of ensuring that compatibility is maintained going forward. And also for brand new libraries, they can start writing their library and see everything that fails, and they have a nice kind of checklist of what to implement. Yeah, again, you can hear more about this library in the talk, but this is using the hypothesis library for testing. Yeah. Next up, we have Array API Compat. This is a compatibility layer for existing libraries. And this basically gives you new namespaces that wrap around the array namespaces to make them compatible. Some, like NumPy, actually most of this is implemented in NumPy itself. It's pretty close to fully compatible, so these wrappers can be quite thin. Some of them, like PyTorch, are a bit bigger. For example, the expand dims function in the standard is called unsqueeze in PyTorch. Cool name, but it's not the standard name. So array API compat.torch, when you call expand dims on that, it will delegate to torch.unsqueeze under the hood. And yeah, this is really important right now for consuming libraries because they don't need to worry about the incompatibilities that might still exist in the array libraries themselves. But in the future, this might go away. Maybe we get to a point where every library is fully compatible. But yeah, it's sticking around for the time being. We also have helper functions in this library. There's quite a few, but definitely the most interesting one is called array namespace. And this shows how we're using it in SciPy to actually make these array agnostic functions. So this is Whiten from scipy.cluster. And in the past, we would have just been using NP, NumPy functions here, and just assuming that the input is a NumPy array, because that's what SciPy worked with. But now, we call this array namespace function on any of the input arrays to get our array namespace that we need to work with, and we call this XP. And then later in the function, where we would have used NumPy, we're now using XP. And yeah, this is a pattern that's repeated all over SciPy right now. There's a few other things in here that might not make sense, but we'll get to them. Moving on, though, to Array API strict. This is another thing for consuming libraries. It's a strict minimal implementation of the standard, and it's a testing utility. What you can do is run Array API strict arrays through your test suite, and if you're relying on unspecified behavior that maybe exists in NumPy, exists in PyTorch, but it doesn't exist in the standard, your tests will catch this, and they'll fail, because they're not implemented in this library. For example, here's one of our tests in SciPy. Most of our tests are now parameterized by XP. So we run all of the tests over all of these different namespaces, and one of those namespaces will be Array API strict. And then if you're using, and then we create those Array API strict arrays, pass them to the function, and yeah, everything works like that. Again, we have some other things here, like we've recreated some parts of numpy.testing to work with all of these different types of namespaces. I'll come back to this. Moving on to the fifth library, we have Array API Extra. This is another thing for consuming library developers, and it builds on top of the standard. So the standard is trying to define what is an array, what does an array library need to implement to really count as an array. But of course there's lots of extra things that might be useful for lots of libraries, where it's kind of going a bit past what you need to count as an array, but there's still things that could be reused quite widely in the ecosystem. And we've started building up a lot of these things from SciPy and scikit-learn right now, where we've had to make them array agnostic ourselves, but they aren't really specific to the domain of our libraries. They're quite general. So, for example, finding the set difference of two arrays. This is quite easy to implement in terms of what's already in the standard. But yeah, we can do it in this common place, and then it can be reused everywhere. We also have tools for lazy backends and read-only arrays. So, for example, there's this xpx.at. Here we have the same function in two different implementations. The bottom is a Cython kernel for NumPy, and the top is the brand new implementation which works with all of these different types of arrays. The bottom is using in-place updates, which is not going to work with read-only arrays, but yeah, this function in the top handles that and can do things like this. We also have lazy apply. This will apply an eager function lazily for these lazy libraries. And finally, we have some testing utilities right now, mainly towards things we need for lazy libraries, but like I said before, we have recreated some things from numpy.testing, and we're hoping to get this stuff in here soon. Final library to mention is Array API typing. We do have experimental static typing support for the standard. It's still in very early development, but the development is active. And yeah, if you're a consuming library that wants to adopt the standard, but everything in your library is typed, then you can look forward to this. Just to close out with a bit of status, where are we? In the array libraries, you can see what we have here. I won't go into full detail, but we have pretty good support across most of the major libraries. And yeah, there's lots of smaller libraries, kind of upcoming libraries in heavy development here that are getting in on the party. In SciPy, we have experimental support. It's been here for quite a few releases now, and we just keep expanding the API coverage. You just set this environment variable, SciPy Array API. We're vendoring these libraries currently, Array API Compat and Extra. And yeah, we're testing against lots of different libraries in our CI. Pixie is really nice for making our GPU jobs there. Yeah, that all works nicely. We also have documentation, and it now comes with API coverage tables. So you can check the parts of SciPy that you're using in your library. Does this support JAX yet? Does it support the GPU? Does it support JIT? Yeah, that's a handy tool we have for consuming libraries. Another thing to mention in SciPy is that it's not all Python. We actually have a lot of compiled code, and the standard doesn't really help us here. It's a Python level thing. So there are some different approaches here. Not to go into full detail, but we have a discussion right after this on dispatching, which is one of the key frameworks that we're going to need to handle this nicely. So if you're interested, definitely come along to that. But one option is actually, and we did that for scipy.spatial.transform. The existing implementation was largely in Python for NumPy. What we did is we split it up to have like a Python API at the top level, which then uses Python for NumPy or uses this array agnostic implementation for other array types. Yeah, we saw some nice benchmarks here, where for very small arrays, the Python kernel for NumPy is super fast, but then it's very slow getting up to large data, and the GPUs, especially JAX, do extremely well here. Scikit-learn 2, similar story to SciPy with experimental support. Also lots of tests, lots of different devices, and yeah, API coverage is coming along nicely. Various different estimators and other helper functions, and yeah, massive speedups as well being observed there. And there's also documentation, which you can find at that link. We have some other projects as well. These are just some ones that I found searching through GitHub of who's using Array API Compat. Still not too many right now, but it's really nice to see that people are kind of taking on the initiative to start adopting it themselves. And yeah, you can absolutely follow them and get in to doing this yourself. And yeah, come and chat to me if you would like to get started with that. Also some bonus projects. Not really going to talk about them in depth, but MArray, I have a poster on this. Come and see that this afternoon. And quantity array, if you work with units, we have a prototype for adding units to any array backend. Yeah, we also have a discussion on units tomorrow, so you can come along to that. And finally, looking forwards, what's next is mainly more adoption. Now that SciPy and Scikit-learn have got a lot of API coverage, there's still a lot left to do, but there are a lot of libraries which depend on them that will now be able to get started themselves. And yeah, like I mentioned earlier, we would like to upstream some testing utilities and keep working on static typing support. We have a sprint. If you'd like to contribute to Array API Extra, please come along on Friday and we can do that. Or also SciPy, you could work on Array API standard support in SciPy too. Or Scikit-learn. And yeah, thanks to all of these people, all of the contributors to the projects here, Ralph Gomez for leadership of the consortium, Patrick Roddy for the talk template, and yeah, the EuroSciPy organisers and volunteers, and all of you for your attention. Thank you.
So, do we have any questions from the room?
Hey, thank you for the nice talk. I'm wondering, the NumPy version 1 to 2 transition, a lot of the work was done with, for example, this rough plugin, which could automatically transform code. I was wondering if an approach like that would also work for moving from code that depends on one specific library or one specific array provider to more generic code.
Yeah, this is something that I've thought about before. It would be really nice to get some automated tooling that could do this. Definitely possible to implement this for some easy cases, and see how far you get. Nobody's started working on it yet, as far as I know, but yeah, it'd be really cool to see if somebody took that on.
Yeah, I have a question that's maybe a bit more about sort of the community work, right? There's like this XKCD comic about like, oh, there's like 17 ways of doing X, so someone should invent a standard, and the result of this is now there's like 18 different ways of doing X, so how does like Array API kind of make sure that it's actually being used as a standard, and are there like competing efforts to do that?
There aren't any competing efforts that are tackling the exact same case that I know of. One option is to just dispatch for everything, even Python. So you can just say, this is my API, and I'll make a plugin framework where you can come along and register your implementation and use that instead. So you could go down that approach, but there's a lot more to it than this kind of automatic, you just detect the namespace and use it. And yeah, in terms of, is it just another thing? Well, it's nice that SciPy and scikit-learn are already very committed to this. So I think now that we have the kind of core of the ecosystem there, yeah, it should be nice to see some expansion out.
Really enjoyed the talk. I was just wondering, when you talk about a common implementation for the different array libraries, is that if the individual array library doesn't implement it themselves? Because I'm sure that maybe specific knowledge about that array library, I think back to Luke's talk on the BLOSK arrays, where the compression is where it's dealing with compression, where having a custom implementation of the methods is desirable.
Yeah, so one thing you can do is, if you're a consuming library, you can have your standard implementation, your array agnostic one, which works with all array types, but then you can also maintain custom implementations that you use for some array types. So if you know, really to make the most out of JAX, I want to be calling these special things over here, then yeah, you can maintain that separately in your library. But then for these other array types that you've maybe not put too much thought into, but that you would like users to be able to use, you can use the standard implementation.
And maybe thinking on the provider side of things. So I guess when you talk about the common implementations, that's on the consumer side of things? Oh, okay. No,
so
what's
common for the array libraries is the API. So we tell you, this is what you take in, this is what you give out, and this is your behavior. But the array libraries are free to implement that however it makes sense for their device or their memory models, whatever. Yeah.
Gotcha. Okay, thanks.
So about the static typing, does this also include a way to have shape information in the static typing system?
The plan is yes. It's not done yet, but Joran, who is working on shape information for NumPy arrays in the NumType repo, he's also going to be working on array API typing, and yeah, we'll see if that makes it there.
Nice.
So nice talk. I am representing the BLOSK project, that is a multidimensional container for compressed data, and we are trying to adapt as much as possible to the array API. But I haven't seen BLOSK tool listed in the list of libraries that is supporting them. So is there a way to onboard on this effort somehow that we are missing? Because we are just reading the documentation and we try to adopt it as much as possible. Thank you.
Yeah, sorry for missing you. There's absolutely no kind of onboarding that you've missed. I just didn't look thoroughly enough. So yeah, just come and chat to me, and yeah, we can kind of open a discussion on the Array API repo. Maybe you can talk about how you're finding it, adopting it so far, any challenges you have. Yeah, that would be a good way to get involved in the community. But yeah, just come and chat.
And maybe add up Array API test to test if BLOSK is compatible or not.
Yeah, so the comment there was just you could add Array API tests into your repo. I don't know if you already have that, maybe, but you can start testing in CI and you can kind of maintain a list of X fails of things that you're expecting to not quite work yet, but that you could work on, yeah.
Maybe one last question.
How do you work on this whilst also doing undergrad?
Standing in the queue for lunch is a good time to scroll GitHub. I do not do much work on coding whilst I'm studying at university. It's mainly kind of reviewing things from people and seeing what they've done. In my vacations, especially over the summer, I try and put some work in. But yeah, it's rewarding to be able to come to conferences like this and speak about it.
Thank you. Let's find the speaker again.
Stay here.
Oh, is it here?
Oh, is it here or is it the other
I thought
room?
it might be upstairs. I haven't been upstairs.
Yes, probably it's on the upstairs.
It's 241.
Yeah. I haven't thought
Okay.
about it.
Hello.
I'm just here to see if everything works.
I hope so.
No tak, pierwszy to poszedł bardzo dobrze. Tu schodami albo windą. Są tam znaczki.
Should I see signal already?
I mean, there is something there, so looks good. Dish.
Nice.
Yeah. If you want, you can also plug in this USB thing for you to.
Yeah. Sorry, it's too small.
Working.
Excellent.
Perfect.
Thank you.
Here's the mic, unless you want that one.
Which one?
This one. Whichever you prefer.
I actually prefer this one.
Okay, sure. There were some technical difficulties with it during the first session, but okay, if it happens, then we can maybe switch those.
Oh, hola.
You go just by Juan or Juan Luis?
Juan Luis.
Juan Luis?
Yeah.
Okay. All right, so it's my pleasure to introduce the next speaker.
Sorry for this.
Juan Luis. He has done a number of things, maybe too much to announce now. He's worked in consulting, data science, as a software engineer, and he's also active in the open source community, and he's going to tell us how to make our Python code run faster using Rust. Looking forward to the talk.
Thank you. Can you hear me? Yes. Okay, well, thanks a lot, everybody, for coming, and let's get straight to it. So, first of all, although this is not news to you, I think it's mandatory to start this talk talking about whether Python is slow or not. Does it matter? When does it matter? And I want to focus on Rust, which is a relatively new language, although not so new anymore, that's making the rounds because it's getting very, very popular to create extensions to Python libraries. And then I want to do a little bit of a demo and jump to conclusions. So first of all, a little bit more about myself. There's some photos here that are not showing up. Okay. Yeah, that's me. So originally, I'm an aerospace engineer, but I've been working in the tech industry for most of my professional life. I'm passionate about tech communities and sustainability. I'm at the moment in between jobs. I've been working as product manager for McKinsey for an open source product for a little bit more than a couple of years. I was developer advocate at Read the Docs for some time as well. And as my side project, I've been very involved in the Python community in Spain. I was one of the founders of the Python Spain nonprofit and organized the first 7 editions of Python Spain. And now I'm organizing the PyData meetups in Madrid. So if you ever are in the city, please come and visit us. And yeah, I've been contributing in the past to the SciPy and PyData ecosystem, not so much anymore. I hope I can resume. And yeah, so about our question, whether Python is slow. I don't know if it happens to you, but there's this table. What's happening? Well, I don't know what's going on, but let's continue. Sorry, this is very annoying.
Is this happening on your laptop as well, or only on the big screen?
Only on the big screen. No, sorry. It's happening on both sides. Well, anyway, I'll manage. I don't know if it happens to you, but from time to time I see this paper making the rounds, especially on LinkedIn, seems to be a thing. It's a paper written in 2021 that ranks programming languages by energy efficiency as a proxy of runtime performance. And you can see there the C and Rust programming languages on top, which set the baseline. And then at the sad bottom of this table, you can see Python over there with Perl, Ruby, and so on. And so usually people use this table to say that, you know, we're wasting so much energy doing all this AI and data science in Python and so on and so forth. And I get very upset whenever this paper makes the rounds because, yes, Python is slow, but that doesn't mean that the Python ecosystem is slow, right? So there we go. The truth is that the community has found reasonable ways of coping with this for the past 25 years or so. We're this old already. And for example, this is a screenshot from the SciPy GitHub that shows that SciPy is made up of many different compiled languages aside from Python, right? We have C, C++, Fortran, Python, and so on and so forth. And so the truth is that sorry, I know this is very annoying, but I don't know what's going on. Maybe like this. Okay. So it turns out that there are too many ways of making Python faster, right? You can use NumPy, Python, Python. There's literally too many of them. And of course, you can write compiled extension in some of the languages, such as C, C++, and so on. Why there are so many options? Because each of these has pros and cons, and there's no silver bullet, right? In fact, my first experience contributing some compiled code to SciPy didn't go really well. This is a screenshot from a pull request that I sent 12 years ago now, and it's part of SciPy.integrate. So the ODEINT function was written back then in Fortran 77, and I made the audacious bet of trying to upgrade that to Fortran 90. I made many mistakes along the way. I was an open source newbie back then, and some backwards incompatibility issues prevented this from being merged. But most importantly, there were no openly available Fortran 90 compilers for Windows back then, and I had no idea about this. So this pull request was lingering for a couple of years, and then it never got merged. And so I was very sad about that, but I kept being interested in performance things in Python, and that is why I started trying all the alternatives, and eventually I landed on Numba, which is a compiler for Python that does just-in-time compiling. And in fact, in the previous EuroSciPy that I attended in 2019, I came to talk exactly about this thing, about how can we make Python faster. without sacrificing readability, right? And 6 years later, I come here again to talk about the same thing, but from a very different lens, because it's been a while since I last used Numba. I've been working on other things for the past few years, and fast forward to 2025, I've been thinking that what if the bad part of compiled languages is not the language itself, but the tooling that we have around it, and the compiler support, the IDE helpers that we get, and so on and so forth. So what if there was a compiled language that was modern, that produced binaries that don't need a runtime, that integrates seamlessly with Python, and that has awesome tooling? Well, and I think the answer for this is Rust these days. So enter Python Rust. Sorry for this. There we go. So it's funny because in the couple past Stack Overflow surveys that we had, the last one that was published a few days ago in 2025, and the one last year, Python and Rust have been respectively the most desired language and the most admired language, which I think it's really interesting, and it makes it a perfect couple to combine both. But first of all, what is Rust exactly? In case you haven't been exposed to it yet, I took this sentence from the Chromium project that says that they found 70% of the serious security bugs were memory safety problems. Long story short, this means a pointer that is pointing to a location that no longer has any data, or some bounds that go unchecked, and things like this. And so Rust was created in 2006 precisely with this focus of trying to address memory safety issues by using a very interesting mechanism. So they don't have a reference counter, or they don't have some sort of runtime. They have something called the borrow checker that checks at compile time whether your variables are going to incur into some sort of memory safety issue. But it goes well beyond that these days, and it's becoming a very popular language that is touching on the Python world a lot already. On one hand, we have lots of data engineering and data processing tools that are written in Rust, such as Polars, for example, an alternative to Pandas, Delta Lake, and so on. And also lots of Python tools that have kind of revolutionized how do we develop in Python these days, such as UV, RAF, and so on. It was the first language other than C and assembly to be included in the Linux kernel. This has been very recent. It's permissively licensed, and it's supported by the Rust Foundation, which is a US non-profit. So it has lots of very good things. In the end, why Rust? Well, because there are so many awesome crates. Crates is the name that packages get in the Rust ecosystem. I care more about ecosystems than languages, because syntax in the end is something that you can get used to, but it turns out that there's lots of libraries that you can import from the Rust package registries that do all sorts of things. Then, because many Python libraries already have a Rust core, as I mentioned, because the error messages and the IDE integration are really great, and they help you learn along the way, because it's memory safe, and just for fun, because it's cool. So how to get started? Well, you only need these 3 simple steps. We use Maturin, which is a Python package that serves as a bridge between Rust and Python, and also helps you start with some template code. And then you launch the Python interpreter, and if everything goes well, then this will get compiled, and you will have a Python function that has some Rust implementation. Let me show that very quickly. There we go. Okay, so if we do UV Maturin, 1 second. UV Maturin new. So we're going to use the PyO3 bindings. This is something that I'm going to explain in a second. And the default template has some silly code that just wraps up a simple function that adds two names. So I can give this any project name. I'm going to get here, and then if I do uv run Python, uv is going to take care of creating the virtual environment with the right Python version, installing the dependencies, building the code, and now I have an interpreter here. So if I do from guessing gain import sum as string, then sum as string 2 and 3 gives me 5. And now how does this look like under the hood? Well, if I see what's the constructor here, you see that we have the pyproject.toml. This sets the metadata for my project. Cargo.toml and cargo.log are the equivalent for Rust. So these contain the metadata and the dependencies for the Rust part. And then there's this library.rs that looks like this. So there's some Rust code and some boilerplate to expose this to Rust. My intention is not to give a full introduction to the Rust programming language, but just to make it less scary to the extent that's possible. So, as I was saying, this works by creating this simple directory structure. There's a library that's called Pyo3, which are the Rust bindings to the Python interpreter. So this is what powers this connection between the two. And now usually when I start a project, I make some small changes in the directory structure to make it a little bit more flexible. Before we get to that, a little bit of explanation of what is going on here. So here's how the Rust code looks like. Nothing weird. There's a function definition, and let's explain what is happening here. This line over here is doc comment, so they're like our doc strings in Python. Then this attribute macro is defining a function that is going to be exposed in Python. This is the function definition. You can see that the types are being included here. This means an unsigned integer of whatever size, and this returns a string. And then there is an expression here that marks what the return value is going to be. We don't need a return expression, a return statement. We can just leave the expression there and it works. So far so good. And if we want to make this a little bit more sophisticated and handle errors as well, Rust has a very interesting approach to error handling and returning non-values and so on. So we would be using this PyResult type, which wraps the actual type that we're going to return, but with the option of this returning an error for whatever reason. Then there's this other piece of code that, well, it's doing some dark magic in Rust. I don't want to get into it, but essentially what's happening here is that it's taking this Py module and it's adding a function after wrapping it so that it can be exposed to Python. And you actually don't need to touch any of this, so this is fine, and we get the result that we were seeing in the demo. Now, a few adjustments to this. If we want to broaden the compatibility of the wheels, there's a small change we can do, because if I do now ub builds, well, this is compiling all the Rust code and everything, and it's going to create a wheel that you recognize here is for Python 3.13. And if I want to target different Python versions, then this would mean that I would need to rebuild this wheel for every single Python version and so on. And actually, there's a simpler way of doing this, because if you specify that you want to use the stable API from CPython, then automatically your wheels now become compatible with any Python larger or equal than 3.9, and you would see that in the file name as well. So this is a tiny change. It's one line in the cargo.toml, but it goes a long way. Then the next thing, usually you don't want just some Rust code that is wrapped. Usually you will want also some Python code, maybe to do some preliminary checks or anything else that you want to implement on the Python side. And so usually I favor this kind of structure here. So we will have the SRC part with all the Python modules using the familiar SRC layout. And then I will put all the Rust code inside its own directory so it doesn't clash with all the things that we have. And then after this, we will need to make a few adjustments. So we will need to declare that the Rust module is going to have its own file length as a private module, just so that people don't accidentally import the Rust functions directly. Then we will need to add some extra information here on the Rust side. And then in the init.py, we can import everything from Rust code and then absorb the doc strings and so on. And finally, just as a matter of convenience, then we can improve the PyProject.toml so that UV detects when the Rust code changes so that a rebuild is triggered. And this is it. Other than this, it's mostly implementing whatever you want and continuing with the development. So before I do a quick demo, any questions about this? Okay, we have some time at the end, I hope. So let me quickly get to that. Okay, so I created a small package with some experiments that I called roads. There we go. All of these materials are online, by the way. And what I did here was experiment with a few problems that in the past I had been working on with Numba, and then try to compare what was the effect of adding Rust. So there's a couple of those here, of course, because of my history developing Polyastro, Python library for astrodynamics. I included an orbit propagation example as well, but I want to focus on this one here, which is a interesting example. This is the formula for the plate deflection after applying a point load. So essentially what happens when I push the table like this. And I say it's interesting because you see that we're doing a double summation here. And this is the displacement in one specific point. So if I want to calculate the field of displacement, so what's the shape of the whole plate after applying the force, then I need another couple of for loops. So essentially we have four for loops in here, and you already know that in Python this is going to be massively slow. So very quickly, how does this look like? So if I go to the Rust code in here, where I created this plate displacement that holds the formula for the displacement of just 1 point. And as you can see, for mathematical code, this mostly looks very familiar. There are some parameters here with the types, and then I am executing the mathematical operation here. Sometimes I have to cast some of the values because Rust is very strict with the types. Another interesting thing is that every mathematical operation is a method, not so much a function. So for example, if I want to compute the sine or the cosine or something, then you see it's dot sine, or the power is dot pow e, so with an integer exponent. And then I have another function that essentially runs that plate displacement formula for every point in the mesh of the plates. But you don't have to stop here because Rust has very powerful abstractions for parallelization. And so what I did here was using a Rust crate that is called Rayon to add another version that does parallelization. So essentially, because each of the displacements is independent from each other, it's trivial to parallelize. And so if I now go to the terminal to see how does this look like, then I'm going to create some test data here with this number of points, and actually I'm going to increase it a little bit for more dramatic effects. And then I want to create the fields, and I'm going to import all the functions. I included the NumPy implementation and the Rust-baked implementation. So if I now try the pure Python one, it's going to take a little while, hopefully enough for me to finish the talk. Otherwise, if we get too tired, then I can just cancel it. And actually, this is the NumPy decorated function. Let me wait. No, I got too impatient. Sorry. No! Well, let's try again. Not so ambitious this time. With fewer points. There we go. Okay. So I come again. Now, hopefully this should be quick. Okay, so the NumPy function is 200 milliseconds. If I try to use the pure Python function, as expected, this is slower. Not that much slower, but because we don't have enough data to notice the difference. And now, if I execute the Rust function without parallelization, just the serial, you see that it's more or less on par with the NumPy implementation, which is good. But then, no, it's the other way around. If I use the Rust implementation that is parallelized, instead of what I had before, which was 200 milliseconds, now I have 28 milliseconds. So it's 10 times faster. So as I said, all of these examples are online. And of course, for more dramatic effect, we see the actual displacement of the plate, which looks just beautiful. Things look plotly. And that is it from my side. So some conclusions. Integrating Python with Rust is straightforward. Granted, you need to know a little bit of Rust, but not too much because numerical code is not that crazy. And rewriting slow code fragments in Rust, I think it's a very effective strategy to accelerate Python code. So again, all the materials are online. Thanks a lot for your attention, and I'm happy to take any questions if we have time. Thank you.
Thank you, Luis, for this very nice talk. Do we have any questions from the room?
Just a quick one, I think.
I'm also quick.
Hi, just a quick one. Thanks for the demo, it's very interesting. I noticed that, by the way, I don't know about Rust at all, other than what you've shown, but you demonstrate the speed increase by parallelization by using map in your Rust code. What are the statistics roughly, or sort of summary of how fast Rust is when integrated with Python for non-parallel operations? I know you showed one example. Is it worth using Rust for non-parallel operations or non-parallelizable?
As with any optimization question, the boring answer is it depends, right? So implementing this Rust version is a little bit of work. And so if you're saying that you have a bottleneck somewhere, then it does make a lot of sense. I also showed that NumPy did a pretty good job. And the good thing of NumPy is that you don't need to learn a second language, right? You can decorate your Python function and it works. So if for whatever reason NumPy is not enough for you because you're beyond what NumPy can provide, or you want to squeeze it a little bit more, then I would definitely have a look at Rust.
If you were redoing Polyastro now, you said you did a lot of it with NumPy. Would you do it with Rust instead?
Very good question. In Polyastro, the bottleneck was no longer the algorithms themselves, although, well, actually, I take it back. We got pretty decent performance But there was somebody that wanted to squeeze it even more and run lots of orbit propagations in parallel and so on. And in fact, one of their discoveries was that we were abusing NumPy arrays for very small fragments of data, and he proposed to replace everything with tuples, which was very shocking for me, and it meant essentially rewriting the whole library. And so I said, well, no, sorry, but I'm not taking this. So probably I would look at those kind of problems and see if Rust could help. But mostly I would be looking as well as trying to add some physical units machinery that's outside of AstroPy.units, because AstroPy.units tend to have lots of overheads, and we managed to avoid that for the most part, but we were still bound to that. So yeah, there were a couple of places where we actually needed to squeeze performance a little bit more, and probably I would be looking at Rust. There's already a good Rust library for astrodynamics, by the way. So maybe we could just wrap that.
Thank you for the talk. In the example you showed, I wanted to ask about NumPy compatibility of Rust, because you've shown that you were importing NumPy in there. Is it a crate in Rust, or is it actually the Python NumPy?
Thank you for the question. I forgot to mention it. Indeed, there's a NumPy crate maintained by people other than the NumPy core team that act as bindings for NumPy in Rust, which means that when you call the Python codes, you can actually pass NumPy arrays, and you get back NumPy arrays as well. There's a few types that are included here. You see there's like a read-only array of dimension 1, read-only array of dimension 2, and so on. So you have to be very deliberate about what exactly do you want. But yeah, it works on a two-way street, and it's really great.
And the second question, because I also have some projects that heavily rely on Numba for threading or parallelization, and I wanted to ask if it's possible to also include node communication like MPI, the Rust code that will be used from Python.
Yeah, I'm not very familiar with MPI and so on. My guess is that there would be some sort of crate to provide that. Also, if you already have Numba code that works, since Numba can accept an FFI function, then probably you can combine Rust parts with Numba parts, and it should be mostly transparent. So maybe you can do the rewrite gradually instead of just throwing everything away.
I'm not ready to write this too much. But I was just wondering because, well, there are limitations for Numba, right? Like, first, it's not that easy to do MPI with Numba without living G blocks, and you know. So I was just kind of wondering if, like, what is the limit of using Rust bindings?
Yeah, for the MPI, I would need to check. Probably this Ryan crate. Crates has something that would be interesting for you, but I'm not sure if they mention MPI at all, at least not in the README. So, answer, I don't know.
Thank you very much.
Yeah, I don't see any more questions, so let's thank the speaker again.
Thank you. Hello. Thank you.
Yes, I will.
So I'm going to introduce you, and then I'm going to hold up some signs with like 5 minutes left, 2 minutes left.
Okay, thank you.
If you notice, there's also this.
Somehow my. Okay, good.
Okay, welcome to the last talk of this session. My pleasure to introduce Jan. Jan used to study cognitive science and computational neuroscience, and I think like many computational neuroscientists, he got hooked on Bayesian inference and machine learning along the way, and he's going to talk to us about simulation-based inference, which is this approach that can be used when problems are really complex so that they become mathematically intractable. My prior expectation is that this is really complicated and scary, but hopefully I can update that prior after hearing the talk.
Great intro, thank you. Hi, my name is Jan, and I want to talk about Pyro and SPI, so how we can unlock hierarchical Bayesian inference for complex simulators. And about me, I'm the maintainer of the SPI package, or one of the maintainers. I have a background, as said, in machine learning and neuroscience in Tübingen, and where I focus on AI for science, so developing or using current AI tools to accelerate scientific discoveries. And at the moment, or now, I'm a researcher at Transfer Lab, which is part of the Applied AI Institute for Europe. And it's a non-profit where we do open source AI research and AI education. And this talk has a lot of different concepts that build on each other. So I want to go through these concepts step by step. And I want to use an example for that. It's a very simple example that has been used to kind of demonstrate what hierarchical Bayesian inference is about. And it's about a cookie factory, or the cookie factory problem. The scenario is that we have a cookie factory with 5 locations, expected in place, and they produce chocolate chip cookies, and they somehow differ in the amount of, or the number of chocolate chips in the cookies. So there might be a global recipe, but each location kind of uses their own interpretation of this recipe, so the numbers are different per locations. So we have these chocolate chips in the cookies, and we have samples of cookies from each location. And now we want to understand the difference between the locations, so we want to estimate the typical chip count, like chocolate chip count per cookie or per location. And the challenge is that there might be some local patterns, but also global patterns. And this is a nice, like a hierarchical inference setting is a nice approach for this problem. So again, the data, we have 5 different locations, and we have chocolate chip samples per location. And we can see on the plot that the location, they differ a bit in their average distribution of chocolate chips already. Okay, so how do we model this? Usually, like the probabilistic approach would be that we assume some tractable statistical model. In this case, because it's count data, we use a Poisson model. So that's our likelihood that we define. And then we can define a prior over the parameters of the Poisson model. So the Poisson distribution takes the rate parameter, so we have to define a prior over the rate, which is, in this case, mathematically it's optimal to use a gamma prior. And then, okay, the question is, why do we even use this probabilistic approach? It allows us to capture the uncertainty that we have in the data and in the process itself. And it offers us a principled way to combine prior knowledge with the data. And later on we see it enables hierarchical inference. Okay, and now the problem, of course, is we have this likelihood, or the model with the rate parameter gamma, and now we want to estimate this parameter given the data that we have seen. One approach would be to use the standard maximum likelihood estimate, so we just maximize the likelihood. It's a standard optimization problem. We do an argmax over our likelihood, and we find the maximum, or the parameter gamma, parameter lambda that optimizes the likelihood. This would be a point estimate, but we could also go all the way and do Bayesian inference, right? So we could try to get a full distribution over the parameters of our model by combining the likelihood. Does it work? Anyways, you can see it here. By combining the likelihood with the prior using Bayes' rule, and we obtain the posterior, so the distribution over the parameter, condition of the data. And then we have actual uncertainty quantification, a principled framework for saying things like, I'm 95% confident that my parameter is in this range. And this can be quite helpful in making decisions, for example, in the cookie factory problem. Okay, now we've already seen the Bayesian inference concept. Now I want to quickly introduce the concept of Pyro, or probabilistic programming languages. And these are just like software packages that allow us to write down these kind of problems in a very efficient way. Right? So for the cookie problem, we just would define one Python function written in this Pyro language that defines the prior in the third line of the function, and then defines the likelihood below. So we sample from a Poisson. We have some observations that we call chips, and then that's all. And then we only have to define an MCMC kernel, so the no U-turn sampler, which is one particular MCMC algorithm, and we can run MCMC to perform Bayesian inference on this problem. So it's really Pyro or other languages like Stan, TimeC, and NumPyro. Their key selling point is that they offer this very efficient way of writing down these problems. So we can use all these out of the box Bayesian inference algorithms. And another thing is that we will see later that Pyro and also the other languages, they have this very efficient way to this plate notation to define conditional independence areas in the model. So if we observe multiple trials, or in this case multiple samples of cookies, then we can just write this down using the plate notation in the model definition, and it will automatically exploit these conditional independence structures in the inference setup. Okay, so that's Pyro. Now, if we want to, back to our initial problem of the cookie factories, we can now take different approaches of modeling this. The first one would be to use a pooled model. So we would assume that all the locations have the same recipe, like one global recipe, and we want to estimate the rate of chocolate chips in the recipe. So we kind of average over all 5 locations. So we just have one prior, the gamma prior, and one Poisson likelihood, and we estimate the lambda parameter of this Poisson. The problem is that we ignore the location differences, right? So we just assume one global mean across all locations. That's the only parameter that we infer. Now the next step would be to use an unpooled model. So we try to estimate one rate parameter for each location. For each factory location, we estimate their local recipe, so their average number of chocolate chips they put in the recipe. That's maybe that's better, but at this point, using this model, we would not share any information between the locations, right? So we would treat each location individually and would estimate, given the amount of data that we have for this location, we would try to estimate the underlying recipe. And now the cool thing about the hierarchical model is that we combine both approaches. So we assume one global parameter, so the group mean across all the locations of all the factories. And for each location, we also have a location-specific parameter estimate. And if we write this down in Pyro, then we have one additional layer of a prior. So before we had this, if you look in the middle, we have Pyro sample from the gamma. So this is our initial, like the prior that we had before. But now we have kind of parameterized this prior, and we have a hyperprior on top. So we have the parameters that we need for the gamma. We have them now parameterized as with another prior, which is again a gamma and an exponential. And now it's like, with this setup, we can kind of share the information between the locations using this hyperprior. It's kind of the information flow can happen through this additional layer on top. And the rest is actually the same. The likelihood is kind of the same. We just sample from the Poisson given the rates that we have sampled. Okay, so that's the concept of hierarchical inference. And just to summarize again, so if we look at the estimate of the means of the unpooled model, for example, we would obtain an estimate for each location, which would be individual for the location, but we would ignore the global recipe, the global mean. And now in the hierarchical approach, if we would estimate the means for each location, they would be kind of drawn towards the global mean in a way. So if you look at location 2, for example, it has a lower overall mean, but it's kind of in the hierarchical approach, it's pulled towards the global recipe, towards the global mean. That's kind of one of the effects of the hierarchical model. Okay, but now comes actually the catch of my talk, because this is all like known and like established. Oh. Good timing for the catch of the talk.
That's the catch.
Okay. All right. So that's the catch of the talk. Everything that I've talked about is kind of known and it's established. But now the thing is, what if the simulator or the model that we are using, what if it is more complex than just the cookie example where you can just say, okay, it's count data, we use a Poisson, everything is tractable, it's fine. What if it's more complicated than that? If we cannot make these assumptions of using a Poisson? It could be like from cognitive science, a diffusion model, or some complicated computer program, some simulation model, climate model, whatsoever. And then our simulator or our model would just take some input, some parameters, and do something, and return data. And we don't have access to the underlying likelihood. Then we wouldn't be able to use these approaches, right? Because in Pyro, we have to define the likelihood in order to perform MCMC. So in traditional probabilistic programming languages, this would not be possible. Now, and here's the idea of simulation-based inference, how it can help us in this case. So the idea of simulation-based inference is that we can simulate data from our simulators, right? We cannot access the likelihood, but we can simulate data. So we use this property of the simulator to generate training data, and then we train a new network to learn the likelihood for us. So we use modern conditional density estimation methods from machine learning to learn the likelihood from data. And then we have a neural network object that can act as our likelihood. So it just behaves just like a PyTorch or Pyro distribution. And we can try to plug this into the Pyro machinery. That's the idea. So this would look like this. On the left side, we have the first step where we train this neural likelihood estimator. So we generate training data from the prior, simulate with our simulator. It can be a black box. We don't have access to the simulator itself. We just get the data. We train NLE using the SPI package. It's really a couple of lines of code. And then we have this estimator object And we define this Pyro model just like before, but in this case we have a wrapper class that wraps our SPI neural likelihood estimator into the format that Pyro wants, and then we can use Pyro instead. So in this class, it's just 150 lines of code. It's mostly shell handling because everything else is already done. So it's one of these cases where the idea is it's simple. We just have to implement a wrapper class, and now we can use SPI and Pyro together. So comparing again the code, it looks really similar. So on the left side, we have the Pyro implementation that we have seen before, the hierarchical model with the 3 layers. And now in SPI, or if we use SPI with Pyro, we have the same setup. So this hyperparameter is the same, the location rates are the same. The only difference is that we are using the neural likelihood. So now instead of sampling from a Poisson, where we make the explicit assumption that this is a Poisson process, we just sample from the SPI Pyro wrapper, and we don't have to make any assumptions about the underlying model. And this works fine. Of course, this is like a toy example. It's simple, but it works fine. Now, this gets more interesting if we have an actual problem where the likelihood is not available, right? So I'm just picking this classical drift diffusion model from psychology, where it's about decision making. This is a complex stochastic differential equation with 4 parameters, and there's no closed form likelihood for that. And now we could go ahead and just sample a lot of data from this differential equation, and then train SPI, and then plug this likelihood that we've learned with SPI into Pyro, and use this powerful, concise framework of Pyro with our DDM model. Okay, that's already it. So some practical considerations. We want to use this approach if we have complex simulators without tractable likelihood, right? And then usually in setups where we have hierarchical and grouped data structures, multiple experimental conditions. And of course, there are some catches. So we have to be able to generate a considerable simulation budget, so for training SPI. And of course, we have to make sure the neural network training converges, and we have to perform some validation and diagnostic checks. But if all this checks out, then it's really feasible to apply this with Pyro. And of course, I mean, if you can write down the likelihood, if you can make these assumptions about your data that are tractable, then it's better to use Pyro. But if you cannot, then it's really a good idea to try out SPI. And I think I'm really happy about this implementation now, that we have this bridge from SPI to Pyro, because there are many applications across domains. And of course, in these domains, these hierarchical models have been used already, but always with some assumptions about the underlying models. And now we can drop these assumptions or use more complicated models and use SPI. All right. So the key takeaways are that, so if you didn't know this before, then the first 2 are important also. So we have probabilistic programming languages that help us to write down Bayesian inference in a very concise way and use standard Bayesian inference methods. Then we have hierarchical models that really help us to capture local and global patterns in data. And then with SPI, we can use these approaches even when we have a model without a likelihood. So SPI and Pyro kind of combine both strengths from both approaches. And with that, I want to thank Juan Aldous for this cookie example that I found in a nice blog post explaining hierarchical inference. I also want to thank Seth Exen, who actually implemented this approach, or this Pyro wrapper in SPI during the hackathon this year. And of course, the communities behind SPI, behind Pyro, and also behind EuroSciPy. And I want to say that we at the Transfer Lab, we currently have a job opening, so we're looking for an AI research engineer. And we have a booth outside in the hall where you can participate in a Python quiz, and you can actually win a mechanical keyboard. So that's quite cool. with that, thanks a lot for your attention.
Thank you, Jan, for the talk. Any questions?
Thank you for your talk. I have a question about the case when the distributions are conjugate. So you can write the posterior likelihood. So is using your library the same good as just deriving the formulas and implementing it yourself? So, or does it work with? So what does this underlying algorithm?
Yeah. So if you can write down, if you can make the assumption of a particular model, like the Poisson model, and you can also make the assumption of the corresponding conjugate prior, then you're kind of fine, right? So you could use it, you could solve it on pen and paper. So if you have the likelihood and the conjugate prior, everything is solved already. And then, so that I think that's one step. And then if you have the likelihood and some other prior, then you can use Pyro for that. So if it's not conjugate, but for all the other cases where you don't want to make any assumptions, then that's the place where SPI makes sense. But for the conjugate case and for the likelihood tractable case, it would make more sense to use Pyro. I'm not sure whether doesn't make sense.
Ask if it's possible to use your library instead of writing just conjugation on the data. Just if it has provided this functionality.
Yeah, you can. Of course, you can. You can use SPI in any case. But if you can write it down, it doesn't make sense to use SPI because, of course, you introduce some errors because you're approximating things with new networks. So my advice would be.
No, so it's not mathematically true then. That's the question. So it's not just understanding the distributions of conjugate and trying to.
Okay, I think maybe I'm missing the question, but I'm happy to talk afterwards. Yeah.
Thank you for the talk, it's very nice. I guess, full disclosure, I'm a developer for PyMC, and I was curious why you like the Pyro, why you use the Pyro for the project, what you like about it versus PyMC or versus Stan, I guess, is like the gold standard in this field.
Yeah. I have no preference at all. So I just happened to talk to Seth, and we were thinking about starting with that for Pyro, but I would be totally open, and I think it would be great to do the same wrapper for PyMC. I'm not so sure because SPI is written in Torch, so there might be some things we have to do in terms of the back end of PyMC, but let's see. Let's talk.
My question is super related because I was just going to ask whether that wrapper that you presented would it also work for NumPyro. I think the only difference is that I think NumPyro is in JAX underneath and Pyro is in Pyro.
Yeah, and same answer basically. So it would be really cool to have this for NumPyro and PyMC as well, but we would have to, the wrapper would likely be a bit more involved, not just shell pending, because we would have to kind of change the backend. But it's a nice project. We could just, like a good solution would be to just implement NLE in JAX or basically in JAX, and then we can do it.
Thank you for the great talk. I've once heard something similar that was called approximate Bayesian computation. Is this then basically the same, or?
Yeah. So approximate Bayesian computation, ABC, is kind of the let's say classical approach of SPI, where it's mostly based on rejection sampling or sequential Monte Carlo methods. But that's just naming convention, right? So we could also call this ABC. I think a couple of years ago there was kind of this shift in calling this SPI. There was also another name called LFI, likelihood free inference, but this so somehow the convention now is to call it SPI.
Okay, cool to know. And so, from my understanding, so every time you like the algorithm NAS or this molecular Markov chain in Pyro, then calls your model, then is the time when you do this 1,000 samples, right? So it's
no, we do the training before, so we only have to train once. So we train SPI or this neural likelihood estimate. We train it once, like kind of outside of Pyro, and then it's ready to be used. So even if we construct a different model, so say we first use a pooled approach, and then we change our mind, and then we use a hierarchical approach, so we write down a different Pyro model, we do not have to retrain SPI, because the likelihood is trained on single trials, so it's kind of the core thing, and it's ready to be used. So there's no, also it's not slower, so like maybe a bit slower than Pyro, but we don't have to retrain along the way.
Okay, thanks.
Sure.
Okay, I don't see any more questions, so maybe the last one.
In the applications examples, you mentioned A/B testing. Do you have something to recommend to read more about how it can be used for A/B testing?
I have nothing specific in mind, but there I can actually recommend PyMC. So PyMC marketing, I think there's even a new package, or a recent package, where they explore different models or application examples, and then I think this would be a good source for inspiration.
When you say A/B testing, do you also mean calculating statistical significance, for example, like analyzing A/B tests? Do you also mean for that application?
I think so. If you can write down a model for the A/B testing pipeline, like a probabilistic model, then that's all you need, right? So then you can do anything with that. You can do full inference, or you can do statistical tests. So yes. Yeah.
Okay, let's thank Jan again. And now we have lunch for the people that joined us today. To get there, you need to go over the coffees and turn left to the adjacent room. Or you can just follow the crowd.
Thanks for the intro. That was good.
Pleasure. Who did you work with in Tübingen?
With Jakob Macke. Do you know people in Tübingen?
Ja, ich habe studiert da Biologie.
Echt? Cool. Ja.
2011 bis 15.
Ah ja, okay. Ja, das war vor meiner Zeit. Ja.
Aber ja, ich kenne jetzt nicht viele Leute irgendwie aus dem Machine Learning Umfeld. Aber hast du da...
Ich habe promoviert.
Promoviert und studiert? Wo?
Nee, studiert habe ich in Berlin. Ich war kurz davor, in Tübingen zu studieren. 2015 habe ich mich dann entschieden. Oder 14 oder so. Dann nach Berlin zu gehen stattdessen.
Aha.
Ja.
Ja, ich habe in Tübingen studiert und in Leipzig promoviert.
Ah, cool. Ja. Und was machst du jetzt?
Ich bin an der Uni Bonn als Research Software Consultant, also arbeite mit anderen PhDs, helfe denen bei so Softwaregeschichten, mache Workshops.
Ach cool, und ist es auch im Biofeld oder auch
Neurowissenschaften.
Neuro, okay.
Ja.
Ah ja,
cool. Genau, also ziemlich breit.
Ja.
Wir sind Teil von so einem Netzwerk, das heißt IB Health, das geht so über NRW verteilt und sind quasi der Software-Support. Also meistens ist es irgendwie, PhDs kommen auf uns zu und sagen, ich habe hier das Paper gelesen, die benutzen irgendwie das Modell und ich will das auch machen und weiß aber nicht genau, wo anfangen und dann helfen wir denen.
Ja, das ist cool, weil das war auch immer so also es klingt so, als wenn ihr einfach versucht, dem Umfeld zu helfen, mit Software
Genau. Deswegen ist es immer cool, wenn ich irgendwie viele verschiedene Talks sehe, weil dann kann ich irgendwie, dann habe ich es schon mal gehört und weiß irgendwie, wenn das Problem kommt, da gibt es irgendwie eine Library dafür und so.
Ja, cool.
Sehr gute Präsentation.
Danke.
See you later.
See you. Hey.
Hi. Wir können auch Deutsch reden.
Cool.
Ich spreche auch Deutsch. Oder Englisch, was dir lieber ist.
Deutsch ist fein.
Mit einigen Leuten, mit denen ich auf Deutsch reden könnte, rede ich auf Englisch. Das ist,
im Arbeitskontext?
Ja,
also,
nee, noch nicht mal. Okay, ich lebe auch aber in der UK, das ist nochmal eine andere Situation.
Okay.
Mit Deutschen dort rede ich einfach auch auf Englisch. Was ich fragen wollte, der entscheidende Part, wie SBI hilft mit Intractable Likelihoods, da bin ich nicht mitgekommen, was genau die Lösung ist. Also wir haben die Data Parameter Pairs und wir benutzen ein Neural Network. Und dann kannst du wiederholen?
Das war auch sehr kurz gekommen in dem Talk.
Ja,
aber,
das würde mich interessieren. Was ist?
Ja, okay. Ja, cool. Also, genau, wir können quasi unser Trainingsdatenset selber generieren vom Simulator. Ne? Wir samplen einfach von Prior die Parameter und dann übernehmen wir alle diese Parameter mit unserem Simulator.
Also den Prior, den
können wir selber definieren. Also,
da suchen wir uns irgendwas.
Das ist so ein bisschen so wie Student-Teacher. Also du hast ein System, das erzeugt die Daten, anders lernt das jetzt. So? Also oder habe ich das ganz falsch verstanden?
Das kommt vielleicht danach, wenn wir das New Network dann anschauen. Aber erstmal, das Trainingsdatenset können wir uns selber generieren. Also wir samplen von dem Prior. Den Prior definieren wir irgendwie mit unserer Domain Knowledge. Wir wissen jetzt irgendwie, in dem Cookie-Example wissen wir, dass es irgendwie... aber also in wirklichen Anwendungen, im Scientific Kontext haben wir ja immer irgendeine Domain Knowledge, mit der wir die Parameter irgendwie eingrenzen können, weil wir haben meistens ja auch ein Modell, was irgendwelche Parameter hat, die irgendwelche Bedeutung haben. Also ein biophysikalisches Modell oder so.
Also da machen wir eine Annahme über die Prior Distribution.
Ja, genau.
Ja, okay.
Was wir vorher schon wissen. Die Parameter können nicht negativ sein oder so. Und dann damit können wir ganz schnell samplen und dann simulieren. Das heißt, der Simulator muss auch relativ schnell sein. Wenn er jetzt irgendwie eine halbe Stunde braucht pro Simulation, dann ist es eher schwierig, weil ich brauche davon irgendwie 100.000 oder je nachdem, wie hochdimensional das Problem ist, auch 1 Million oder so samplet.
Kann ich da noch eine Frage stellen? Und zwar, also wenn wir die Prior Distribution eingrenzen und wir samplen, also hast du da ein paar Beispiele, wie du das spezifizierst? Also das ist das Beispiel gebracht mit, es hat vielleicht keine negativen Values, aber damit das Ganze effektiv ist,
also
ich weiß nicht, wie broad oder wie spezifisch du da sein musst in der Spezifikation von dem Prior.
Also ich würde sagen, du
von der Prior Distribution.
So spezifisch sein, wie du kannst.
Ja,
genau, weil du willst den Raum möglichst weit eingrenzen, weil sonst musst du ja überall suchen im Raum, aber auch nicht zu weit, weil du willst auch die echten Daten irgendwie abdecken. Das heißt, aber in der Praxis nutzen Leute oft halt Uniform Priors. Sie haben einfach Prior Bounds und nutzen die halt komplett.
Das heißt sehr unspezifisch, also eine Uniform Distribution ist.
Aber das Gute ist, dass halt die Bayesian Inference kann halt dann den Bereich lernen, der wirklich relevant ist. Und jetzt kommt die Krux bei SBI, ne? Also wir haben das Trainingsdatenset und dann aus dem Machine Learning Research gibt es seit 5 oder 10 Jahren diese Methoden, bei denen wir mit dem neuronalen Netzwerk eine Verteilung lernen können. Also wir sagen zum Beispiel, eine ganz einfache Ansatz wäre, dass das neuronale Netz kriegt halt die Daten als Input und der Output-Layer ist, wir machen einfach die Annahme, dass unser Posterior, den wir lernen wollen, eine Gauss-Verteilung ist, einfach nur. So, macht erstmal keinen Sinn, aber als einfaches Beispiel. Das heißt, der Output-Layer von einem neuronalen Netzwerk ist einfach nur die Mean und die Varianz von dem Gaussian. Das heißt, das Netzwerk kriegt die Daten als Input und lernt die Mean und Varianz vorherzusagen. Also die Verteilungsparameter. Nicht die Model-Parameter, sondern die Verteilungsparameter. Dann der nächste Schritt wäre, also der Gaussian ist natürlich viel zu einfach als Annahme, aber als nächsten Schritt nehmen wir ein Mixture of Gaussians. Das heißt, der Output-Layer von dem neuronalen Netz muss jetzt, wenn wir jetzt 5 Komponenten haben, muss jetzt 5 Means und dann die ganzen Kovarianzen und die Mixture Weights lernen. Aber damit können wir schon relativ komplexen Posterior irgendwie repräsentieren. Und jetzt seit ein paar Jahren nutzt man eben dann modernere Verteilungsmodelle wie Normalizing Flows oder Diffusion Models oder so Flow Matching Models.
Mhm.
Und das ist eigentlich die Idee. Also wir haben einfach ein Machine Learning Framework, was in allen anderen Bereichen auch genutzt wird. Und das nutzen wir hier in dem Kontext dafür, diesen Posterior zu lernen.
Wo kriegst du da die Ground Truth für den Posterior her? Also woher weißt du, was das ist?
Die gibt es nicht. Das
So,
ist ja das Faszinierende. Das lernt es aus den Daten. Also wir haben ja das Mapping
von der Prior Distribution.
Aber du musst doch irgendwo sagen, wenn du jetzt neuronales Netz trainierst, das kommt rein und das müsste jetzt rauskommen. Das ist das, was du vorher sagst, müsste das doch irgendwie ein...
Also wir haben die Parameter vom Simulator, ne? Die haben das irgendwie, und damit können wir jetzt die Daten simulieren. Ne? Diesen Schritt.
Das verstehe ich.
Den haben wir.
Das ist, glaube ich,
was wir eigentlich machen wollen, wir wollen den anderen Schritt lernen. Also wir wollen ja, gegeben Daten, wollen wir die Verteilung über die Parameter gegebenen Daten lernen.
Aber du bist jetzt, wir reden hier jetzt nicht von der Prior Distribution.
Also ich dachte, das wäre Prior, jetzt bin ich aus der
Ja, ich dachte auch, wir reden...
Nee, also hier kann ich immer...
Das, was wir samplen, ist der Prior Distribution, was wir als Input in das neuronale Netz bringen, ist...
Nee, es sind die Daten tatsächlich. Also das Netz, also wir können von Prior samplen, dann bekommen wir Theta und dann können wir simulieren und bekommen X. Ne, also X samplen wir quasi vom Simulator, also von der Likelihood.
Okay, aber jetzt das Theta ist von der Prior Distribution.
Genau, wir samplen das Theta hier von Prior, stecken das in den Simulator und kriegen dann X.
Okay, und dann haben wir unsere Daten und die speisen wir ins neuronale Netz ein.
Das stimmt, das ist nicht so gut, aber der hat eine riesige Tabelle mit ganz vielen Beispielen Theta und das entsprechende X. Theta und das entsprechende X. Und deswegen haben wir diese Beispiele. Und damit kann das Netzwerk...
Ach so, du machst ganz viele...
Genau. 100.000 oder so.
Ach so, jetzt verstehe ich.
Und das Netzwerk... Ich versuche jetzt... Also das Netzwerk...
woher weißt du, welche du simulierst?
Okay. Das mache ich random, vom Prior.
Einfach irgendwas.
Ja. Das Netzwerk kriegt dann X als Input.
Ja.
Und den zu nutzen, das ist so ein bisschen spackig. Vielleicht schon mal dann, das ist eigentlich Kinder. Das kannst du auch anziehen, das ist abgespannt, kannst mir vertrauen. Nein.
Okay.
Das ist der Vertriebler.
Also das Netzwerk kriegt X und hat dann irgendwelche Layer hier.
Ja.
Und als Output lernt es jetzt zum Beispiel dann den Mean und die Varianz von vielen Mixture Components und kann dann deswegen halt eine Verteilung ausspucken über Theta, die halt Conditional X ist, weil X habe ich reingesteckt und auch noch, die ist ja parametrisiert durch hier diese ganzen Parameter, die ich gelernt habe.
Und das weißt du auch alles, weil du mit dem Zeug SX erzeugt hast.
Nee, genau, das ist die entscheidende Frage. Das habe ich mir auch am Anfang nicht gefragt, wie das eigentlich funktioniert. Das Lernsignal, wo kommt das Lernsignal her? Und die Loss-Funktion ist halt, womit ich jetzt diese Netzwerkgewichte aktiviere oder lerne, ist halt einfach die Wahrscheinlichkeit unter dieser Verteilung. Also der Loss ist, es ist ja nicht mal ein echter Perceiver, es ist ja nur eine Schätzung, ne? Der Loss ist das hier. Also Theta I. Also ich maximiere quasi die Wahrscheinlichkeit von meinem parametrischen Modell, also von meinem Gaussian oder von Mixture of Gaussian, mit dem aktuellen Trainingsensemble. Ich versuche einfach immer die maximale Wahrscheinlichkeit für dieses Paar zu bekommen und dadurch lernt er halt die Verteilung.
Was nimmst du da, also die Parameter, also du hast da jetzt Mixture Gaussian, ne, am Ende spezifiziert. Was würdest du dann nehmen? Ist es immer ein...
Achso, jetzt was sozusagen...
Welche Verteilung? Die Parameter von welcher Verteilung? Also das ist Mean, Variance und dann viele davon.
Ja.
Hier
muss ich nur entscheiden, wie viele Komponenten ich will. Also wie viele Mixture Components, also 5 oder 10 oder so. Ist eigentlich immer genug. Aber Mixture of Gaussians ist quasi auch eher so 2015.
Ja.
Heute macht man halt Normalizing Flows.
Ja, okay,
und
das war meine Frage. Also das würdest du jetzt aktuell machen.
Weil die sind deutlich flexibler als, oder können mit weniger Daten schneller eine komplexe Verteilung lernen.
Ja.
Irgendwelche funky Shapes und so.
Mhm. Ja. Und also du würdest immer eher was nehmen, was sehr flexibel ist und komplexe Verteilungen beschreiben kann.
Ja, genau. Ja, schon, weil in der Praxis sind die Posterior halt schon, also dieses Cookie-Example ist halt super trivial. Aber es ist ja auch eindimensional. Aber in der Praxis sind ja die Modelle